In section 6.5, we are going to be solving exponential and log equations. We had solved some basic exponential equations in prior sections, but now that we have all these log properties, we can use those to help us solve more complicated equations. We're still going to try, if we're solving an exponential equation, to get the bases to match. So if you can get same base, the bases will cancel, and then it's just setting the exponents equal to each other to solve. It happens that that's the same property with logs. If you can get log same base equal to log same base on either side of an equal sign, then you can cancel the log and simply set the arguments equal to each other to solve. However, that's not always possible. If you're working with an exponential equation and you cannot get the bases to match, what you could try doing is taking log or natural log on both sides of the equation. So it's nice when you have an equal sign, what you do to one side, you do to the other. We can actually log or natural log both sides of an equation as well. Now, if it's a log function and you can't get same log equal to same log, then try writing it as log equal to a number so that you can switch it to its exponential form. So just to recap, exponential functions, same base, cancel. If cannot, log, natural log both sides. Log function, same log, cancel. If cannot, get log equal to number, change it to exponential form. In example 1a, we're going to solve 2 to the x plus 1 equal to 4 to the negative x. Now in this particular example, I can get the bases to match as we did before by simply writing 4 as 2 squared. I'll have 2 to the x plus 1 equal to 2 squared in parentheses and then to the exponent negative x. So 2 to the x plus 1 equal to 2 to the negative 2x. Same base, cancels. I get x plus 1 equal to negative 2x. Let's see, I am just going to subtract x from both sides and then divide by the negative 3 to get negative 1/3. I want green. When we're solving exponential equations, you could check the solution to see if it works, but we don't have to check the solution to see if the original equations are defined. However, very important, go back up. When solving our log equations, and this is going to come up later after we're done with the exponentials, when solving log equations, you always have to check your solutions because remember the domain on log functions got to be positive. So if you end up with some possible solutions, you got to plug it back into the log equations to make sure you don't get negative or zero. Let's get back to our exponential equations. We're going on to B. I have e to the x plus 1 equal to 7, and I notice I can never get e and 7 to match. So now I'm going to try to log or natural log both sides. Now, since this is base e on the left, it seems appropriate to natural log both sides. So natural log of e to the x plus 1 is going to equal to the natural log of 7. From log properties, this natural log of e is going to cancel, and I end up with just x plus 1 equal to the natural log of 7. To get the x by itself, I would simply subtract 1 from both sides. And I'm done. This is an exact solution. It looks weird, but it is correct. Now, if I were to put this in a calculator, I would get an approximation, a decimal approximation. I would not get the exact solution. So the reason why we choose log base 10 or natural log when we log both sides is because we can easily put these values into a calculator since most calculators have base E or base 10. I'm not going to approximate it though. I'm more concerned with finding the exact answer, not whether somebody can plug something in a calculator. In part C, same equation, except for instead of base E to the x plus 1, I've changed it to base 10 to the x plus 1. Now I can't get 10 and 7 to match. However, I see that if I log both sides, because remember that's log base 10, then it will match with this base 10 and maybe something nice will happen. So I am going to log both sides. This becomes log of 10 to the x plus 1 equal to log 7. Properties of logs, because remember this is base 10, says if the base and the argument match, they cancel. I end up with x plus 1 equal to log 7. And now I would simply subtract 1 from both sides to get my exact solution, x equal to log 7 minus 1. Again, I'm not going to bother putting this in a calculator. I'm more concerned with exact solutions. So let's build on the difficulty a little bit. Notice in D, I have 2 and 3. There's no way that they can match. And in this case, I don't have a base E or a base 10, so it doesn't really matter if I choose to log both sides or natural log both sides. And just to let you know that in your textbook, or on my lab, they traditionally use log on both sides. Me personally, I prefer natural log because it's less writing and I tend to be a little bit more lazy. So I am going to natural log both sides to get natural log of 2 to the x plus 1 equal to natural log of 3. You may ask, why are you doing that? You're making it even worse. Actually not, because we can use that property 7 and we could bring the x plus 1 exponent out in front. So the problem with solving these equations where the variable is the exponent is it's very difficult to isolate that exponent and get it equal to a number. It's very difficult to solve for an exponent. So we always have to have some sort of trick, like getting bases to match or logging both sides. In this case, when I bring the x plus 1 out in front, remember this is going to be in parentheses, and it's going to be times natural log of 2. So that's going to be equal to natural log of 3. Now, natural log of 2 and natural log of 3, they look weird, but they're just numbers. Put them in a calculator, you'll get some decimal approximation. So the goal is to solve for the x. I want to get rid of the natural log of 2. I'm going to simply divide both sides of this equation by natural log of 2. In here, cancel. On the left, I get x plus 1 equal to natural log of 3 over natural log of 2. And now it's a matter of just subtracting 1 from both sides to get x equal to natural log of 3 over natural log of 2 minus 1. Again, that looks weird, but we solved for x. And on the right-hand side, that's just a number. Notice there is no variable on the right-hand side. Natural log of 3 is a number. Natural log of 2 is a number. Again, this is an exact solution. You could put it in a calculator to find a decimal approximation if you wish. Let's do 2 more examples. Difficulty is going to be a little bit more on these last 2 exponential equations. In part E, I have 5 times in parentheses 2 to the x minus 9 plus 6 equal to 31. Now, I cannot log both sides the way it's written. What I want to do is simplify the equation as much as possible before I decide what I'm going to do, because maybe I can get bases to match. First thing I'm going to do is subtract 6 from both sides to get 5 times 2 to the x minus 9 equal to 25. And then notice if I divide by 5 on both sides, I get 2 to the x minus 9 equal to 5. So now I've simplified as much as I can. Base 2 and 5 No way I can get that to match, so I can either log or natural log both sides. Again, I usually choose natural log. I'm going to log both sides this time just to show you what your book prefers. And if I log both sides, I can now use that property 7 to take the exponent x minus 9 out in front of the log of 2. So parentheses x minus 9 times log 2 is equal to log 5. I would then divide both sides by log 2, which will cancel on the left-hand side. To get x minus 9 equal to log 5 over log 2. And now I would simply add the 9 to both sides to get my exact solution, of x equal to log 5 over log 2 plus 9. Last example with exponential equations. So the 5 and the 7, no way I can get them to match. I'm going to try natural logging both sides because, again, lazy me, don't want to write a lot. I'll get natural log of 5 to the x plus 1 equal to the natural log of 7 to the x. And now on both sides of this equal sign, I can use that property 7 to bring the exponents out in front of those natural logs. So parenthesis x plus 1 times the natural log of 5 is equal to x times the natural log of 7. Okay, so now I have to solve for x. Problem is I've got x on both sides of this equation. So I have to figure out how I can get all the x's together on one side, all these other numbers like natural log of 5 on the other side. I'm going to do an algebra trick. I'm going to distribute the natural log of 5 and get rid of the parentheses around the x plus 1 to get x times the natural log of 5 plus natural log of 5 equal to x times natural log of 7. And the reason why I did that is so I could separate the x from the plus 1. Now I have x times natural log of 5 on the left, and I have x times natural log of 7 on the right. I could subtract x natural log of 5 from both sides to get natural log of 5 equal to x times natural log of 7 minus x natural log of 5. So what I've done here is at least I've gotten all the x's on one side. At this point on the right-hand side, I can factor out the x, and it'll be times the natural log of 7 minus natural log of 5. Natural log of 7 minus natural log of 5, that's just a number. And I could get rid of it by simply dividing both sides by natural log of 7 minus natural log of 5. And then on the right, the natural log of 7 minus natural log of 5 cancels. And I'm done. I have the x by itself on one side of the equal sign. So natural log of 5 over natural log of 7 minus natural log of 5. That's going to be equal to my x. If you had decided that you were going to keep all the x's on the left-hand side, your answer may look a little bit different than mine. Maybe you would have had a negative natural in front of the natural log of 5 in the numerator, and you would have had natural log of 5 minus natural log of 7 in the denominator. But these are equivalent forms. So if you put those equivalent forms in a calculator, you should get the same decimal approximation. So if you're unsure if your answer matches the MyLab answer, then you can go ahead and plug it in a calculator, plug them both in a calculator and see if you get the same answer. So that's probably the worst it's going to get with exponential equations. Having x in the exponent on both sides, so that when you log, you're going to have x's on both sides. You're going to have to do some algebra where you would get rid of parentheses and bring all the x's over to one side, factor out the x, and so on. So let's move on to log equations. So again, whenever we solve log equations, we have to check solutions. In example 2a, well, this is nice because I already have log base 3 equal to log base 3. Don't really care what's inside the parentheses. I got same log on either side of the equal sign, so they can cancel, and I'm just solving x plus 9 equal to 7 minus x. So it should make sense, right? The only way this can be equal is if the arguments are equal, since the outside, the log base 3, is the same. I think I'm going to add x and subtract 9. I would get 2x equal to negative 2, or x is equal to negative 1. Again, I have to check that solution. I have to check it to make sure I don't get a negative argument. If I put in negative 1 for x, on the left-hand side, I'm going to have log base 3 of 8, which is fine. It's not negative or 0. On the right-hand side, I get log base 3 of 7 minus a negative 1 is also 8. So we're fine. And in fact, it is the solution. Log base 3 of 8 is equal to log base 3 of 8. So x equal to negative 1 is a good solution. Looking at b, there's no way I can get log base 2 equal to log base 2. Well, maybe I can, but it might be kind of tricky because I only see one log base 2. So instead of trying to get log base 2 equal to log base 2, what I'm going to do is try to get log base 2 equal to a number and then change it to exponential form. The issue I'm having here is that there's a 2 in front of the log base 2. That can't be there. However, I can simply divide both sides by 2. And then on the left-hand side, these 2's will cancel, and I'll have log base 2 of 4 minus x is equal to 3. So think about what this is saying. If I switch it to exponential form, we have our base 2 to the exponent 3. That's going to be equal to 4 minus x. So base is 2, exponent is 3. I have 4 minus x equal to 8. Negative x is equal to 4, or x is equal to negative 4. Is that a good solution? We need to check. So if I put negative 4 in for x, I get 2 times log base 2 of 4 minus a negative 4 would be 8. And I can use that solution because my log is defined. It's not negative or 0, it's a positive 8. And in fact, this actually is the solution. If you go a little bit further by dividing by 2 on both sides, and then switch it to its exponential form, you'll get 8 is equal to 2 to the third, which is 8 equal to 8. Checks out. X equal to negative 4 is a good solution. So a few more examples and then we'll be done with this section. Example 3, I have 2 times log base 7 of x plus 3 is equal to log base 7 of 1 minus 3x. I cannot cancel the log on both sides, and I cannot cancel because of the 2 in front. Remember, it has to be log 7 equal to log 7, nothing in front. So I could divide both sides by 2, but that won't help me because that'll just be moving that 2 over to the other side, and I'll have 1/2 times log base 7. So instead, I'm going to use property 7. Normally, when we use property 7, we're taking an exponent and we're bringing it in front of the log. But now I'm going to take that exponent or that 2 in front of the log, and bring it up to be the exponent on the x plus 3. So I would write this as log base 7 of x plus 3 squared equal to log base 7 of 1 minus 3x. Now I have log 7 equal to log 7. Again, I don't really care about the argument. I don't care what that is. I just want to get log 7 equal to log 7. The only way this equation can be true is if the arguments are true. If x plus 3 squared is equal to 1 minus 3x. But remember that this is not x squared plus 3 squared. This is x plus 3 times x plus 3. And that will be equal to 1 minus 3x. I get x squared plus 3x would be a plus 6x. And then plus 9 equal to 1 minus 3x. I see that it's quadratic, so I am going to set it equal to 0 by adding 3x to both sides to get plus 9x, and then subtracting 1 to get plus 8, and that's equal to 0. So this does factor. This factors as x plus 8, x plus 1 equal to 0. So our possible solutions would be x equal to negative 8 and x equal to negative 1. Going back to my original equation, I could see right away that negative 8 is not going to work, because look at the left-hand side. If I put in negative 8 for x, I'll get 2 log 7 of negative 5. So that's not going to work. Let's look at the negative 1. If I put in negative 1 for x on the left and the right, my argument won't be negative or 0. It will be a positive number, but I'm going to go ahead and check it just to see if it actually is a solution, or the solution. So that would be 2 log base 7 of, if I put in negative 1, it becomes 2, equal to log base 7 of 1 minus a negative 3, so that's going to be 4, 6. What is that? Can't do my math. 4. Okay, so are these the same? Well, we can take the 2 in front of the log and bring it up as the exponent on the 2 in the argument. So that would be log base 7 of 2 squared, which would be log base 7 of 4. That checks out. And x equal to negative 1 would be my only solution. Okay, a couple more. Let's look at D. So in D, we have natural log plus natural log equal to natural log. The bases are all the same. You cannot cancel the natural logs. And that's because we don't have natural log equal to natural log. I have 2 natural logs on the left and only 1 natural log on the right. It has to be 1 natural log equal to 1 natural log before I can cancel. However, I do see that this is an addition here. Looking at our log properties, remember when you're adding 2 logs of the same base, you can combine it into one, in this case, natural log, where you would just be multiplying the arguments. So now that I have used property 5 to write this as natural log of x plus 5 times x equal to natural log of 2x plus 4, I have 1 natural log equal to 1 natural log. It must be true that the arguments are equal. On the left, I'm going to distribute that x to write this as x squared plus 5x. And that's going to be equal to 2x plus 4. Quadratic. I am going to subtract the 2x from both sides to get a plus 3x minus the 4, so I could set it equal to 0 and see if it factors. And this does. It factors as x plus 4, x minus 1. So our possible solutions would be negative 4 and positive 1. And now when I look at these natural logs in my original equation, I see right away that x to the negative, or x equal to -4 is not going to work because of natural log of x. If you put in -4, the natural log of x becomes negative on the argument and it's not defined. It also won't work for a natural log of 2x plus 4, but all I have to do is show that it doesn't work for one piece and it won't work for the equation. It won't be a solution. But it doesn't work on the right either, because if you put in the -4, you're going to get a negative argument. So let's try the positive one. That becomes natural log of, if we put in 1 for x, it's 6, plus natural log of 1 equal to natural log of 6. Now remember, natural log of 1, in fact, log of 1 for any base is 0. So this checks out. We get natural log of 6 equal to natural log of 6. And x equals to 1 is the solution. Last example for this section, I have log, and it's base 10, so no need to write. Log of x plus 4 minus 1 equals to log of x minus 5. Now I see that minus 1 there. It would be nice if it wasn't there, because then I would have log equal to log can cancel. However, if I tried to get rid of it by adding 1 to both sides, I'm going to just be moving it to the right. It'll still be there. So this tells me that the most efficient way to solve this is try to get the logs together, equal to a number, and change it to its exponential form. So I think what I'm going to do is I'm going to minus log of x minus 5 from both sides. So I'll have log of x plus 4 minus log of x minus 5. So I can get all the logs on one side. And then I'll add 1 to both sides. So that's going to be equal to a positive 1. See the subtraction in between these? That means I can combine these into one log with division. So this would be x plus 4 over x minus 5 equal to 1. And now recall, this is base 10. Now that I have log equal to number, I don't really care what the argument is at this point, I can switch this to its exponential form. So this is, base is 10, so it's 10 to the exponent 1. And it's x plus 4 over x minus 5 equal to 10 to the 1, which is just 10. I'm going to multiply both sides by x minus 5 to get rid of the fraction. That will give me x plus 4 equal to 10 times x minus 5, or x plus 4 equal to 10x minus 50. So now I think I'm going to bring all the x's over to the right. If I minus x from both sides, I get a 9x. And if I add 50 to both sides, I get 54 on the left. Dividing by 9 gives me 6. So x equals to 6 would be a possible solution. We will go back to the original equation. And notice if I put in 6 for x, it seems like a fair solution. Log's going to be positive on both sides. But let me check to see if it actually is a solution. So I get log of 10 minus 1 equal to log of 1. And remember, this is log base 10 of 10. So by one of our properties, that's just equal to 1. So 1 minus 1 equal to log of 1 is 0 by another property. And I have 0 equal to 0. It is a solution. And that's it for this section. Again, if it's exponential equations, try to get the bases to match. If not, log or natural log both sides. If it's a log equation, try to get log equal to log so that they cancel. If cannot, try to get log equal to number and change to exponential form. Just don't forget to check your solutions to see that you don't have negative or 0 in the argument. And that's it.